Okay. Right, hydrolyzed ammonia here, but when we look at the ionic equation, we want the major species that are reacting. When we look at ammonia and water, which side is favored? Which side is the more stable side? The left. Because when we compare the base here, ammonia versus hydroxide, hydroxide is a much stronger base. In Chem 1A, we say no driving force, no reaction, but we know a little bit of reaction, or partial reaction occurs here. And so this is the major species here. And so we wouldn't break this up. This should not be 2 ammoniums and 2 hydroxides. This should be 2 ammonias and 2 waters. Okay.
Would it be wrong if you put 2 ammonia and 2 hydroxide ions and 2 hydrogen?
That would be wrong. That would be wrong. Because if you have hydroxide and hydronium, there's a strong driving force to neutralize. You have strong base and strong acid. You have acid-base neutralization to form 2 waters in this case. Unless the hydroxide and hydronium come from different sources. When I look at this, the hydroxide is coming from here. Where's the hydronium coming from? Water itself. It's not going to happen like that, okay? And so this is very common in the ionic equation to write ammonium hydroxide. We aren't going to write ammonium hydroxide anymore here, even though those are the species reacting. And so it is a little bit awkward because, but it's the same thing, when you look at the net reaction for potassium sulfide, overall, when we added up all those equations, the hydrolysis of water from sulfide canceled out. And that equation was just that solid potassium sulfide reacts with the acetic acid. And so this is kind of the same thing. We're missing some steps that happen there, but we always are missing some steps, as we'll see when we get to kinetics. And all we're looking at, and these are the net overall reaction. Okay? There's a net overall reactions between these 2 reactants here. Does that make sense? All right, and so this changes the spectators here quite a lot, because if we left this here, then ammoniums are spectators, and nitrates are spectators, but if we have this ammonia and water, the spectator is only nitrate. And so we end up with magnesium 2+ plus 2 ammonias plus 2 waters yields magnesium hydroxide solid plus 2 ammoniums. So this will be it. All right, not to say, that's writing ammonium hydroxide, some instructors prefer to write ammonium hydroxide here, so you'll see it. I just have the preference not to.
Some instructors let you write ammonium hydroxide because they want you to see the double replacement.
Yeah, that's true. That's true, so it could go either way, but when you go to purchase a bottle of ammonium hydroxide, you might encounter some difficulty finding it. That's all. But you might find difficulty. I tried to buy some ammonia from a European chemical. I couldn't find it. I thought, how could a major chemical manufacturer not have ammonia? And the reason is they did have ammonia, but they called it nitrogen trihydride. So I had to get some nitrogen trihydride. I bought it in this gas, in pure form. I wanted high purity ammonia. I wanted high purity ammonia so I could make a super base, a super base, which is a base much more powerful than like amide or methide,
Yeah, I looked up super bases out your class, and I found that it's really weird. It needs a lot of the main group metals, not metals, like the metals,
Yeah.
as well as a lot of the acids like the cotton.
Right. The super base I made is just you take ammonia, you liquefy it, so you make liquid ammonia, and then you dissolve sodium metal in it, and then it glows like a blue, brilliant blue color. It's almost like fluorescent. And then
That's really
you use it to
cool.
react. Yeah. But it's kind of like it's amide and free electrons in there. So sodium amide. But there's super bases and super acids. Super acids, you know, at USC, there's a person who works, George Olah, professor there at USC. He won the Nobel Prize not too long ago for his work. He's looking at super acids to make all kinds of things, like synthetic gasoline and other stuff, you know. What were the applications for the super bases that you looked at?
I don't remember a lot of the applications. I mainly looked up what elements that they are used, and they're not ones that I would think generally find in base. That's why I was a little surprised.
Yeah, there's just exotic species, so that's why you don't really have to worry about them too much. You don't encounter them so much. A question?
I heard salts of antimony, like antimony trifluoride, will be like a super acid.
Yeah, there's something in the homework. I think that's one of those, but I'm not that familiar with antimony trifluoride. Antimony has some very interesting chemistry, though. A very just weird behavior, as I recall. Remember, I made an antimony compound, but I can't remember the formula. It was so long ago.
But the antimony is this chemical thermal is SB.
Yes. So it doesn't behave quite like it should behave like arsenic and phosphorus, but it behaves a little differently. It has got a lot of electrons, so it has weird optical properties.
I really like this problem.
You really like antimony?
Yeah, that's my favorite element.
Oh, good. Good. That's nice to have a favorite element. Platinum is a good one. Platinum or gold. My least favorite element, I'll tell you. Some of my least favorites. Thallium. Sulfur. I dread sulfur because, you know, sulfur stinks, but organic sulfur compounds are the worst. I used to, you know, its skunk odors consist of a lot of organosulfur compounds. So I used to work with thiols, which are alcohols, but sulfur-based alcohols rather than oxygen-based alcohols. And my lab partner spilled a drop of thiol on his brand new sneakers, tennis shoes, and they had to throw them away because there's nothing you could do to get rid of the odor. You could bleach. Usually bleach works pretty well because it will oxidize the sulfur. Okay, there it goes. All right, let's go to this second PowerPoint here series, and we're going to look at acid-base reactions now. For acid-base reactions, we have three types: the Arrhenius, Bronsted, Lowry, Lewis. Arrhenius is minimal. You know, Arrhenius. Does anybody know the Arrhenius definition of an acid? Arrhenius.
Isn't it when in water it is either hydroxide or acid or hydrogen for base?
Yeah, right. Yeah, hydronium for acid, hydroxide for base. And that's all. It's either H plus AQ or H3O plus AQ and OH minus. And so the only Arrhenius acid-base reaction would be H3O plus hydroxide, or H plus hydroxide yields water. And so Arrhenius, let's not spend any time. Bronsted Lowry, this is what we're going to spend time with. This is probably what we're going to spend the most time with. But as far as definitions go, Bronsted-Lowry isn't the most concise or the most broad or the most comprehensive definition of an acid and base. The most comprehensive definition of acid base is Lewis. And so we really only need one. We only need number 3. But the problem with number 3 is that it's more difficult to deal with. Bronsted is a subcategory of acids and bases. This subcategory is very easy to deal with. Very easy to predict the products of the reaction. But we don't get all the acids and we don't get all the bases. So for example, CO2. CO2 is considered an acid, but it's not a Bronsted acid. It's a Lewis acid. Well, Bronsted, all we have to do is transfer a proton from the acid to the base. The acid is a proton donor, the base is a proton acceptor. So we're just looking at H+. And so when we figure out these reactions, we transfer a proton, determine if there's a driving force. Also, we have to look because sometimes multiple steps will happen, like a diprotic acid or triprotic acid has more than one proton. And so we might have further reaction. But for the first step, this is the method. We do what's called an inventory. I'll talk about that. Then we determine the strongest acid and the strongest base present. Then we transfer a single proton from the strongest acid to the strongest base. The strongest species of the species most likely to react because they're going to be the most reactive. Determine the driving force if necessary, and then repeat if further reaction occurs.
Wait, is that the steps to solve the Bronsted-Lowry base problem?
Yeah, acid base. Now, we have 2 different methods of solving problems. We have the metathesis method versus Bronsted. In the metathesis, you always do full reaction. We just always do it full reaction. Meaning this, if I have H3PO4 and sodium hydroxide, I'm not going to just neutralize one. So for example, I don't just say, okay, I'm going to neutralize one of the hydrogens and make sodium dihydrogen phosphate in water. This is typically not done. In metathesis, you go all the way. That is, we're going to neutralize all the hydrogens. And so we're going to form sodium phosphate or trisodium phosphate. Look in detergent bottles and 3 waters. So to balance this, we'll need 3 sodium hydroxides. And so this is typically what's done in metathesis. In Bronsted, we take a different approach. In the Bronsted approach, we just neutralize one at a time. Tilt this. So we neutralize one at a time. In Bronsted, we would only do this, and Bronsted always yields the net ionic equation, so we just have one hydroxide that would neutralize it. And so we'd form dihydrogen phosphate plus water. Okay, then we'd look for subsequent reactions from here, but we only do it one step at a time. One step at a time. Here we do full reaction. Same reaction. Right. All right. So let's go back to this and let's just do some examples. It's not that difficult to do. Oops. All right. Phosphoric acid and aqueous sodium hydroxide. I'm going to do this using the full Bronsted approach. phosphoric acid plus sodium hydroxide. And what the first step is inventory. So we need to figure out what the major aqueous species are, or non-aqueous species. There's a solid. H3PO4 is a weak acid. So do weak acids, do we ionize them in solution? Complete no. And so the major species would be H3PO4. Sodium hydroxide is a soluble salt. And so we ionize it with sodium ions and hydroxide ions. And so these are the species we have so far in solution. But we're missing one. Do you know which one we're missing? Water. We're missing water. Water is an acid and it's a base. So we have to consider that. Okay, then we go back to this one. We determine the strongest acid and the strongest base present. And so when we look at phosphoric acid, that's an acid. Sodium ions, are those a proton donor? Not a hydrogen, do they have hydrogen to donate? Would they accept a hydrogen? So for example, are they proton acceptor? Sodium plus H plus yields NaH2 plus.
No.
Does that look good to you? It looks bad. And so they're not a proton, so we call them neutral. And neutral, they aren't going to react. Hydroxide, yes, base, but hydroxide is very tricky because hydroxide is also a acid. It's amphoteric. It's base. It's a much better base than it is an acid. But you know, these reactions always depend on what you reacted with. And so this is amphoteric. Same with water. Water is both an acid and base. Water is equally good, whichever way it reacts. And so we have three acids. And do you need the chart to figure out which of these three acids is the strongest? Or can you just look at it and determine?
I could tell that phosphoric acid is strong.
Yes. How?
Because if hydroxide is a strong base, it must be a weak acid. So it's strong.
Yeah, this is really not much of an acid, and this is not very much of an acid. This would be the best to neutralize base. Which is the strongest base? Hydroxide. So something like this we don't really need. And so we end up with that reaction here. And we aren't done with this reaction because we have to figure out if there's a driving force present. So we can rewrite this. See it. So all we do is we transfer a proton from the acid to the base. And so we're going to have H3PO4. Transfer a proton to hydroxide. So hydroxide puts a proton on it. Leaves H2PO4 minus in water. All right. Now we don't use the chart because we already figured out this is our acid, this is our base. Dihydrogen phosphate's amphoteric, so it can go either way. Water can go either way too. Which way it goes depends on the reaction. And so we have to look. If we were to reverse this reaction, would dihydrogen phosphate gain a proton or lose a proton going backwards? It gains a proton. The proton acceptors are the base. So dihydrogen phosphate's acting as a base. When we look at water going backwards, does water gain or lose a proton going backwards? It loses, so that's the acid. Okay, then we compare the two acids. Which is a better acid? Phosphoric acid or water? Phosphoric acid. What's a better base? Hydroxide. So we have a driving force here. All right. For us, for this first part of Chem 1B, we aren't going to do any extra steps. We're only going to do one step here. The next step would be, we look at what's left over. And if there's extra hydroxide can attack either of these. This is a stronger base, so it'll attack it. Or a stronger acid, sorry. This is a stronger acid, it'll attack it. But we'll just leave it at one step. So that's all you have to worry about for right now. Multi-step we're going to do later when we get to chapter 16. All right, try this one.